This is the third video on regression, and in that case we're using regression in a more general sense, which means just predicting numerical values for some variable, but in that case still we're using some methods that come from the linear regression model, so I think that this is something that can be put together with the classical regression models. And we'll see two different but related algorithms, which are called, I won't say regression trees, and other kind of algorithms which are model trees. And both are based in mixing two things we have seen before. One is what we did with decision trees, where we were doing partitions on data. So you have recursive partition, and then because now you have numerical variables instead of categories for the prediction, you mix this with ideas from regression. So mixing those things, you get this new kind of algorithms. I will start with regression trees. So this is well known because it comes from the 80s. So this is a almost classical machine learning method, and the idea about regression trees is that you have your data, which is numerical, and let's say you want to predict some variable which I call way to follow the notation we were using with classical regression. And now what you do is start like in the decision trees algorithms by doing partitions based on, for example, entropy, to get parts that have homogeneous behavior inside. And in that case you start doing the partition, so you get rules, and then for the first variable, maybe if it's lower than some value you get one part, if it's higher than the other you get the other part, and so on. And at the end you'll have a tree. And in that case, when you do decision trees, what you expect is the data that's living in those parts is very homogeneous in the class. So if the class has just a few values, in every final leaf you have data where the class is always the same, or almost always the same. So in that case you have a very high probability of finding a given value for the class, and then this is the value that you predict. If you do this in that case, what happens is that the data that you have here is given by different values of y. So what you want in that case is to be homogeneous in y. That means that you don't have a large variation in the numbers here, but all go around the same middle value. And in that case, what you do at the end, you have this partition, and that's the model, because now you predict from here for every leaf you predict the mean value. You sum and divide by the number of elements in that leaf, and this is your prediction. And if you want to connect this in some way to classical regression, you should notice that the most simple prediction you can do is by a constant. So this is like a polynomial of 0 degree. Remember that in the linear basic ax plus b estimator you have the constant b, the intercept, so this is part of this estimator, and now you are using just the intercept with nothing else, no more variables, because the role of the other variables has been to get you the partition. And now you have this set of values, and your prediction is the best one. That for a constant is, if the predictor is, if the estimator is a constant, the best constant is the mean value. So this is something easy to prove, and one of the first things that you see in the classical theory of estimation regression. So in that case you are doing this prediction, which is the mean, which is almost common sense. So this is essentially how regression trees work. The algorithms, the basic algorithm is called CART. This is from the 80s. This is from the 80s, and the meaning of the letters is classification, and regression trees. So for classification, it's meant what we saw as decision trees. So this first part is decision trees, and then the next part, regression, is what I'm explaining now, which is for numerical, for predicting numerical variables. And in R you can run this algorithm. There are many implementations of this algorithm, and we'll use a package in R which is called R part, which means recursive partition, something like this. So this is the package we'll use to do the regression trees in the example we'll see after the explanation. Well, the other algorithms we consider here are the model trees. Those are more complex than the regression trees. Here the idea is similar to what we are doing with regression trees, which is doing the partition. So you start in a similar way by getting a partition using entropy or other indicators, and then what happens is that instead of getting very homogeneous leaves, what we get is pieces of data where you can perform a classical regression, so a linear regression model. And so you have a tree with the rules for the partition, but also at the end, for every leaf, you have an estimation y, which is a linear model, not just a constant as before, which was just like the mean, but now you have some combination of the variables. So some coefficients for the variables, something like this. So at the end, if the tree is large, you get a lot of models. So you have a model for every leaf, and then the prediction is better than in the regression trees, because not only have you done the partition, but you at every part still have the power of a linear model. So what are the properties of those models? First, you need, so this requires lots of data, because you have the partition, but still you should be able to perform a regression on the leaf. So you need enough data in every leaf to do a regression, and also you have a lot of leaves, so this requires a large size data frame in the terms of the program. So this is not suitable for when you have small data. That's one thing. And another thing is that even if the performance, for what the error concerns of this, is better than the other models, and at the end you have the rules, but you also have the models, so what you have something which is more complex to interpret, more difficult to interpret, because the model is complex. So in that case you have a model that put together is complex. So it's not so easy to interpret things in that case. And the model trees is more modern than the regression trees. This comes from 1992 algorithm, which is called M5 algorithm. This is by J.R. Quinlan. And then there is an improvement in 1997, which is called M5 prime. M5 prime. You'll see that in R the name is written M5P for P for prime. So this is the model we would use in the example. There is a version that you can use in R, which is from the R. You need the R Weka package, and when you have this package you can use the algorithm. And in fact I ran the script that I used the past course, and I got problems with this algorithm because it seems to work, but the numbers are not right, and I couldn't figure what's the problem. I think it has something to do with maybe the versions, but I tried to update all the versions for R and the package, and still it didn't work. So I will comment on this in the script part of the video. But anyway, I I will explain the syntax because it's very simple of how to run this. And one last thing to understand a bit better what's happening here. Imagine some data, let's say for two variables, one predictor and the y variable, and you have the dots here, so this is a visualization, a scatter plot for the data you have, and suppose you have points like this, and something like this kind of shape. And as you see here, the problem with a typical linear regression is that you only predict for one given x. You have the coefficients fixed, so you must adjust to this variation here. So in that case, what you would get is something like a line here, because usually the estimation goes to the middle, the mean of the sections, and then something like this. And this is an estimation which is good for this part here, but not for the rest of the plot. Instead of this, if you let me repeat the plot here, it's the same plot, x, y, and then the points here like this and this, and let's say that this point here is x0, and then you have y0. So you could build a model. Let me change color. You could build a model as a model tree in a way where you start dividing by this line here. So you do first x less than x0, and in that case you are at the left, and here you could fit this part here with a linear regression. So this is the fit one part, and if not, you have the tree starting here. If x is more than x0, you have this part here, and you know that you cannot do a linear fitting for all these points, so you enter a new rule that divides like here. So if y, so we are now at this part here, and then you look at y less than y0, you have this part where you can fit, call this fit 2, and then here you have y larger than y0, where you can fit this part like fit 3. So at the end you have three different linear models that work on different parts of the data. So the tree, the three leaves of the tree are this part, and this part of the data. So the tree works by getting to every part, and then in every part you have the fit 1, fit 2, or fit 3, depending on the area where you are. So this is an explanation of what's happening in the model trees and why they can be useful in some cases, because when data is very complex, you might have this kind of behaviors where you need different fits in different parts. And of course, this is something where the previous case, the regression trees are not good because you only predict there with the mean, but here you need more than the mean. You need the local fitting with a line in the different parts. So this is the explanation for the Model 3's algorithms, and the next part of the video will be running an example to see how you can do these models in R. Okay, I'm opening the script for regression trees and model trees. That's it. And so you need to run the script, which is called regression trees, and then the data you need is white wines CSV. So this is an example about the prediction of the quality of wines. So you have data with properties of chemical properties of the wines, and then the quality which is given by people trying the wines. And I'm loading the data frame, and let's see. Now you have this variable, and this is the structure, and you can see that you have 12 variables. The last one is quality. This is the target that you want to predict. So this is a number, I think, in the range from 0 to 10. And the other variables are the properties of the wine, like acidity, sugar, density, pH, alcohol, and so on. So you want to predict quality using those other variables, and I define n as the number of instances. So notice that you have almost 5,000 observations here. This is just the names of the variables. And let's look at the quality variable histogram. So that's it. And this is the histogram. And the empty spaces are because it's an integer variable, so you only have integer values. You can see that the mean is around 5, and it has some kind of normal shape. And okay, for the training I'm using 3750. This is more or less 75%. And now I'm breaking the data frame to get 2 parts, one for training and the rest for test. Since I'm just dividing without random sampling, I check that the quality has the same mean in both parts, and it's so because it's 5.9 and 5.9, so it's the same mean. And okay, that's it. We'll do first a regression tree. For regression trees, we use which is called the CART algorithm, and we're using the implementation which is in the package called rpart. So you need this package, and I think that this is default, but there are two packages that we'll use in this script that are not default, but I think you have installed before. One is rpart.plot and the other one is rweka. And let's see. Let's compute the regression tree. The name of the algorithm here is called rpart, same as the package. And I'm running this, passing to it the data frame, Wayne train, and then the variables is the one to predict is quality, until the dot means that we are using all the other variables. So I run this, and sorry, I didn't load the library rpart. Now I run here the model, which I call rpart, Control R. I just call the model, so that's it. You have here the model. This is the tree, and at the end of every leaf you have the mean of the quality variable. The terminal nodes, as here they tell you, are the ones with the asterisk. So here you can see the structure of the tree because of the indentation, gives you the levels, and here you have the terminal leaves. So at every leaf you have part of the data. Remember that you had like 5,000 almost values, and for every part of the data here you have the mean value. If we try the summary gives you more information, and let's go there. Okay, so you have the call, and then you have a lot of information here. You have the variable importance, how important is very variable, by every variable. So you can see that alcohol is very important, and also density, and other ones like residual sugar is not so important, and so on. And okay, so you have here information on the tree about the how you do the splits in the tree for every node. So that's it. You have a mean square error at every leaf. This is because you have the numbers and then you have the mean, but then you can compute the deviation of the data in the leaf. And so this is all the information you have here. And now I will use the other library, the package rpart.plot. So this is related to rpart, but you must install it as an independent package. So I'm reading the library. And this is to visualize the trees, because it's not very clear just by looking at all of these numbers how the tree behaves. So it's better to have some display of the tree. And the basic instruction is rpart.plot, and with no much options, I run this and I get this default form of the tree. So here you have the rules to split the branches of the tree.
And here you have the final leaves, and the percent of data that belongs to the leaves. So this is one visualization of the tree, but you can enter different options for this. So for example, if I put here fallen leaves false, that means that here all the leaves are at the base level, so they have fallen, and you can do this without they going down in the graphics. And also you have other options that you can study by using the help on the command. So you have this type equal 3 and the extra 101. So I run this now and I get the same tree but with another kind of display. Okay, so you have the rules now written in the branches, and every leaf at the level it appears, and also here you can see the number of instances going to this leaf and so on. Also, I'm doing the prediction now using the test part of the data frame. So I use the typical predict command with the model and the data frame. I call this P part, the P from prediction. So the M is for model and the P is for prediction. So this will be a vector with the predicted quality values, Control R. And now I use to study the error, first the correlation between the actual quality values and the predicted values. So if this is the correlation coefficient, if this would be very close to 1, the prediction would be very good. And if it's more close to 0, then the prediction is bad. And here you have a middle value, 0.536 for the correlation. And I also computing the mean square error I do this by using the mean applied to the square of the difference. So this sums the values and then divides by n. Control R, and to understand this number, because here this is like the square, you should do the root to have maybe a better scale, or if not, compute the absolute value that has the original scale, which I have here, the mean absolute error. So we'll do the mean absolute error to have a number that has the scale of the original variable. Control R. And this is not very different from the other value, 0.6. And remember that the quality value is an integer from 0 to 10. So that means that you are doing the prediction with a mean error of 0.6 in this number. So the prediction is good in the sense that you are not very far from the point, the actual value, but not with a great precision. Okay, so something which is a 7 could be predicted maybe between 6.4 and 7.6. So that's the thing here. But this is enough to illustrate that kind of models. And so you have the rules that you could use to interpret this. This comes from an article about the analysis of wine quality, and I don't remember now. I will check if at least the reference is in Atenea or maybe the whole article. And the original article, they used not those algorithms. I think they used maybe neural networks or maybe super vector machines, and they had more error than the one we have in these models we are running in the script. Not a big difference, but a small improvement. And also in that case, the model might be interpreted, and this is interesting because you want to know what give you the quality of the wine. So this is something you have here. You wouldn't have something like this using neural networks or those kind of algorithms. And the final part is getting something more complex, which is the model tree. Models trees are something which is similar, but then you are running in every leaf, not doing just the mean, but running a linear model, a classical regression. And this is where I saw some problems, but I'm just running it as it is, and I will check later if I can understand what's happening, but by now, because I think the past year this was working with no problems. So I load the library, Arweka, and now I'm computing the model. The algorithm is the M5, and this is the improved version from 1997, which is called M5 prime. So M5P is the name, and the syntax is the same than before. So I'm sure that the problem is not in the data, because in the first part is running okay. And I run the model. This runs with no errors. And now I look at the model, and here you have a very large output, because the tree has a large structure. And notice that you have 163 rules. That's a lot. And I go up, and that's it. And okay, you have here the structure of the tree with the rules for getting to the leaves. That's all the tree. And then after this, you have the models at every leaf. So for every rule, at the end, you have a linear model, and here you can see the model, which is the set of coefficients, and the variables that are multiplying the coefficients. And I know that those numbers are not right. I had a reference for this coefficient, for example, that was very different. So I didn't expect this 0.04 here, and so that tells that something is not maybe right. But the model has run apparently with no errors, and so you have this lot of models, linear models at every leaf, so the coefficients go changing. And okay, and after this, what I do is the summary, and the summary is where I see that this is not right, because you can see here that the correlation coefficient is negative, and this shouldn't happen when you are doing a prediction. The minimum thing is that the correlation is positive. If not, this doesn't make sense. And also you can see that the mean absolute error has no sense, because you are predicting an integer from 0 to 10, and here you are getting a very large numbers. And in fact, I don't have this in the script, I'm just doing it now. I did a histogram of the prediction, which is P underscore M5P. Oops, what happened? Oh, sorry, I still didn't make the prediction, so I'm doing first the prediction. Control R. So the numbers before were just over the training part of data. Now I'm doing things on the prediction, so they should be not very different, but a bit worse than what we had here. And so now I run the histogram for the prediction, and here you can see that this makes no sense because this is negative and with some very large values. So I don't know really what's happening here, because there is nothing that can go wrong because this is very simple in syntax, and I know the data is correct for the first part. So I checked for the versions because I had with Arweka a warning about the versions, so I just updated my version of R. So now I'm running the last version of R, which I installed before, and this is version 4.0.0. So this is a major change in the version. And then I install, well, I didn't install, but I just copied and then I updated the packages, which was like a pain in the ass because it gave some errors at some point, and it was like a lot of work, but at the end it's apparently okay. And the problem is the same that I had before with these numbers that make no sense, and these predictions which are completely outside the range of the variable I'm predicting. And then I compute the correlation, and you can see that it's consistent with what we had before, so it still doesn't make sense, and it's a bit worse than before if you forget about the sign, because before was 0 to 2 and now is 0 to 0, so less correlation in that sense, but still a negative correlation. So I know that this number should be something like better than what we had with the regression trees. So it's close to, I think is 0.5 something, I think, and this is not what we are getting here. So I say here I have the histograms. That's it. So well, I have the computation of the errors, but I know that this doesn't make sense. So those numbers are completely nonsense in that problem. So I don't know. I will check for this and try to understand where the problem resides, but today I just didn't find anything, and I'm leaving it this way. So with this we finish the part on regression and also this mixing of regression and trees, and so we close this part, and the next video will be about neural networks.